Hey everyone, welcome to the September edition of the Pyroscope community call. We're doing things a little bit differently this time, where we figured that there are many folks out there in general who may not be actually familiar with what profiling and flame graphs actually are. So we figured this time around we would go into that. If you have any questions, please ask questions inside of the chat. If for whatever reason it does not let you ask anything in the chat, you may need to go and create a channel. So yeah, please ask questions along the way, and I will give it over to you, Brian. And not me, that's me. Hi.
Hi everyone, I'm Brian, an engineer on the Pyroscope team. So today we'll be talking about an introduction to profiling and flame graphs. And this will be the first installment and hopefully a series of installments of introductory to intermediate material targeted towards profiling in general. So our agenda today: what is profiling? What is a flame graph? How we read flame graphs, and some tricks of how to read flame graphs using Grafana's Profiles drill down amp. And then we'll end with a Q&A if there's any questions that come up. So the question everyone has is, what is profiling? But maybe a better thing to ask first is, why do I even want profiling? Aren't logs and metrics and traces enough to satisfy our observability needs? Traditionally, metrics has filled the role of answering the question of what went wrong, logs the why, and traces the where. Profiling slots into this hierarchy by answering the question of how. So Grafana has a product called Grafana Pyroscope, which is a continuous profiling solution. So that means we will continuously profile running applications and build out flame graphs or build out profiles for that application. This means you can query a profile for any given point in time and not for discrete points in time, or ask for discrete profiles. And so of these profiles, really can help complement the additional questions of the what, why, and where by giving you even more information and insight into your programs. And I want to touch on this before we get too deep, because a common question is why do we want to do profiling when we have tracing? So I want to kind of compare and contrast the problems each solution solves, where profiling describes the cost of running a program, tracing describes the lifespan of a request or a transaction. So profiling is definitely oriented towards understanding costs, resource costs of your program, and tracing is a little bit more event-oriented to describe when events happen on which service and what their relationship or lifespan of that event might be. Profiling is very statistical in nature, and we'll get into that in the next few slides, whereas tracing is very deterministic. When you establish the starts and ends of each span that build out your trace, as your code executes, those spans will always start and end in the same places with relationship to each other. Certainly, tracing is statistic to some degree. From a sampling perspective, you may decide to accept a trace or not accept a trace, but once you've accepted a trace, the structure of that trace is very deterministic based on where you've selected to start and end your spans within your program. The data for profiling is an aggregation of stack traces, whereas the data for a trace is a tree of spans. Likewise, like I just kind of alluded to earlier, the data for profiling is collected by sampling the stack traces, and data for tracing is collected by manually instrumenting spans. This is Tracing oftentimes will have those spans start and end at the beginning, at the function boundaries, but this is not necessarily required. You can obviously have a span start and end in the middle of a function or around any logical operation your program might perform. And lastly, profiling identifies the how portion of latency and slowness. So it'll tell you what specific functions were being used aggressively to cause slowdowns, whereas tracing will point to the where. It'll tell you which service, possibly which general logical operation that your program performs might be slow, but it won't tell you which specific functions. Won't always tell you which specific functions cause that slowness. So we get back to the original question of what is profiling. So profiling is a way to measure how a program spends its resources. So your common profilers, most profilers will be able to measure common resources like CPU or memory. Some profilers can measure even more exotic resources like mutex or thread pools. We build a profile by sampling stack traces during program execution. And we aggregate these stack traces together over some period of time to form what we call a profile. And continuous profiling just means we always do this, so we never stop trying to build that profile. What does profiling help with? Profiling is quite useful in helping generally gain an understanding of precisely how your code behaves in the environment where it runs. So you don't need to set up an artificial environment to try to get observability hooks inside your program. You can have it running in production, and profiling can help you understand its behavior in production with production workloads. So this includes identifying the hotspots in your program. You can use profiling to help validate where you suspect your hotspots might be. Discovering code that may be inefficient. So if you had an assumption on how code ran, but it wasn't correct, or maybe it was correct, profiling can help validate those inefficient code, those assumptions about the inefficient code blocks. And it can also help by expose bottlenecks. So if you have functions that execute that are slower than they should be, or are constraining your system in some way, profiling can help eliminate those functions. So when it comes to visualizing a profile, there's a few different strategies. I'll review some of the common ones. One is a top table. So we can see that a top table is just a flat list of function names and their relative costs that they contribute to the duration of the profile. So in this case, we can see that we have this insert stack trace function that's a method on the tree symbols object, and this is over the duration of this profile, this was responsible for 4.31 seconds of CPU time, which accounted for 1.57% of the profile. And so I want to say that, and also mention that top tables are really good for finding mins and maxes. You can sort these columns and identify quickly the minimum and maximum of the various columns. So the top tables are really effective at doing this. Another strategy to visualize a profile is through a call graph. So in this case, the boxes represent functions, and the arrows between the boxes represent the stack traces, or the which functions are calling which other functions. And then lastly, we have one of the final popular ways of visualizing profile is using a flame graph. And so here we have a common example of flame graph, and in a second I'll kind of we'll go into depth on how we build this flame graph and how we understand this flame graph. I will say I just want to touch on that there's two common ways that you might see a flame graph in the wild. One is where the root starts at the top and builds its way down, and the other is where the root starts at the bottom and builds its way up. Functionally, there's no difference between the two. It's just a difference of how to render or how to build out the flame graph. So when we read a flame graph, there's two important components to keep in mind. That the y-axis is our call stack depth. So this describes which functions call other functions. And so you kind of get a tree-like structure there. And the x-axis is the cost of the function, or how much resources that function consumes. So it's not timeline. So on the left isn't time 0, and on the right isn't the end time, but rather the widths just refer to the relative cost of that function. So in this case, we can see that our total cost is 4.62 minutes of CPU time, and each one of these sub bars is some component of that total 4.62 minutes.
And I have a question that came up. So the question is, do we use profiling only on code basis, or can we integrate it with infra logging as well?
Typically, you'll want to run your profiling on your own code. There are other systems. That's where you have the most control of profiling. And if that doesn't answer, or if you have follow-up questions, we can always get to that too. Okay, so building a flame graph from a profile. So how do we get from those sampled stack traces to a flame graph? So as an application executes and it's running in your environment, you'll have a profiler running alongside it, which is simply another program. And what that program will do is every 10 milliseconds, it'll ask your program's runtime what stack trace is on the CPU at this point in time. And so the runtime will then respond and provide that stack trace. And so we can see that here we have 5 stack traces that have been sampled over the course of 50 milliseconds. And when the profiler asks for that stack trace sample, it assumes that whatever function is currently being executed by the CPU, or that function at the end of that stack trace, it just assumes that function took 10 milliseconds to run. And we'll see how this makes a difference as that profile gets built. That function may take more or less time, but this is the statistical component of profiling, where we need data over time to begin to build a more and more accurate picture of your system behavior. So the minimum resolution is 10 milliseconds. So like I said, we have stack trace S1 through S5 that we've collected over 50 milliseconds. And I want to touch on that. These bars represent functions in the stack trace. So this first bar might be one function, and then that function calls another function, so on and so forth. And we finally get to this final function, which hasn't called additional functions. And so when we're building this flame graph, we'll take all of those stack traces and aggregate them together into one big bundle. And we call this a profile. And then when we want to render this profile, what we do is we combine all of the common stack trace prefixes. So if we go back for a second, we can see that some of these stack traces share common prefixes, like these 3 functions here match these 3 functions here. So S1 and S3 share a common stack trace prefix of these 3 functions. And likewise, you can see that S4 also has that same common prefix. Now, S2 has a common prefix of these 2 functions with all S1 through S4. And so you can kind of get a sense for how we might combine the common prefixes, all of these stack traces. So when we do this, we can combine these prefixes, and now you can see that how the time no longer starts from the left and goes to the right, where all of our stack traces are unordered. And that's where we lose the orderedness of the stack traces, and it instead becomes the width representing the cost. And so at this point, you can already see, even with these 5 stack trace samples, that we're starting to get to an object that approximates a flame graph. And you can imagine, as we add more samples, that this visualization will only become more similar to a flame graph. So kind of tying this back to some code. So on the left, we have some pseudocode, and on the right, we have a sample flame graph that represents that pseudocode. So we've profiled the pseudocode and we've produced a flame graph. So here you can see in the main function, we have our main loop calls 2 functions, do little and do a lot. And you can see them represented in this flame graph on the left, or on the right, where our main function consumes the entire portion of the total profile, and it calls this do a lot function and also this do little function. And you can see again that time does not go left to right, where technically do little is called first in the code, but it shows up second in the flame graph. So just to reiterate that it's our cost left to right, not the time. So you can kind of visually map the pseudocode to the relative costs commented in the pseudocode to how those costs appear in the flame graph, where this do a lot function, we spend 65 CPU cycles, and then inside prepare, we spend 35 CPU cycles. So you can see that we have 65% in the do a lot, and then we have a smaller portion executing this prepare. And likewise with do little and its call to prepare.
I have a question. Is there a certain amount of so this example is like X CPU cycles, etc. Is there like a certain amount like CPU cycles or time that is like mandatory for it to take in order for it to actually be able to show up inside of a flame graph?
So that's a good question. So here we're being commented about CPU cycles. We actually don't measure most profilers won't measure CPU cycles. They'll actually measure CPU time. But it's kind of a nice way to think about it, how CPU cycles equates to time. There's no minimum amount of time that a function needs to spend on the CPU in order to be profiled, but there is a minimum measurement that the function will be measured to have assumed to cost, which is 10 milliseconds. So even if a function only takes 1 millisecond to execute, if it was on the CPU when the profiler sampled it, the profiler will just assume that it costs 10 milliseconds to run that function. Hopefully that makes sense. So you can't get a resolution smaller than 10 milliseconds. Well, you could, but you can't. I guess a better way of saying it is you can't get a resolution smaller than whatever frequency you sample at. So if you sample every 10 milliseconds, you can't get a resolution smaller than 10 milliseconds. If you sample every 5 milliseconds, you can get a resolution smaller than 5 milliseconds.
So for instance, if like do little only took 5 milliseconds, there's a chance that it may never show up depending on when you are sampling it.
It's possible, but again, if you sample for long enough, eventually you will sample a stack trace that has do little being executed.
Thanks.
And this actually is kind of an interesting kind of side note, which a lot of profilers won't sample at precisely 100 milliseconds or precisely 100 hertz. They'll sample at some, sometimes prime number that's close to 100 to try kind of break typical cycles of landing of things that always fall between the fence posts of every 10 milliseconds. So if you sample at some prime hertz, then you can kind of break up natural cycles that might occur to try to help hit those faster functions. So some techniques to understanding a flame graph. Here we have a slightly more complicated flame graph, and it can be intimidating to try and look at this and understand what you're looking for, what things in this flame graph are valuable. So I want to cover some strategies that you can use to help understand these flame graphs. The first is that nodes with open bottoms represent work being done. So you can see that these nodes that I've highlighted here have no additional nodes below them. So that means they weren't calling other functions to like pass on the work or ask for some additional work to be done. These are nodes that are actually performing the work. So this might be, some computation. You might have loops here that, operate on data structures. But these nodes are important to identify, and you want to look at these nodes to understand if their width is reasonable for the work that is being done in the code. Now, I do want to highlight this doesn't mean that these open bottom nodes are always the last ones in the line. You can see that this one right here has one additional frame below it, but you can see that there's still an open bottom here, which means that this node right here is partially calling a second function to do some work, but it's also partially doing some work itself. So open bottom nodes don't have to be restricted to the very bottoms of the flame graph, but they are the ones that are important to consider when observing a flame graph. Then this is a very non-traditional term, but I like to call them the flames. So these are kind of these regions of the flame graph that kind of visually group themselves into a single flame or a single tree that's independent of the rest of the flame graph. These approximate themselves to processes in your application. And so this isn't process like a Unix process. This is processes in like you have the portion of your application that's serving HTTP requests, for example, or a portion of your application that's performing some kind of batch job. These are like the logical processes in your application. And it's important to keep your eye on these as well and understand their width in relationship to the rest of the flame graph. Does the width seem reasonable in comparison to the rest of your flame graph?
Hi, question.
Yes.
Is the horizontal order of the blocks the order for the execution of the stack frame?
No, it is not. The horizontal order can be changed depending on your flame graph and how the profile is built. So in some tools, the horizontal order you can sort kind of by greatest to smallest widths or vice versa. But yeah, it certainly does not represent if we have this frame coming before this frame, that does not mean that this thing executed before this thing. It just happens to be placed left of it. So the only X component that we really focus on is width in proportion to the rest of the flame graph. But that's a great question. And so if you're running in a garbage collected language or a language with a heavier runtime, it's very often you'll find that you can identify the flame for your runtime. And so this is obviously going to be language dependent. Some languages are going to have a much lighter runtime and thereby their flame is going to be less obvious. This profile is for a Go application. And so we can actually identify the flame which corresponds to the Go runtime. And so this can be helpful too. You might not necessarily be able to directly influence the cost of each one of these functions in this flame. But if you see the runtime flame get too wide, there might be other things you can do in your code to indirectly influence it. For example, you might want to manage your heap memory a little bit more closely, maybe try to allocate fewer objects or reuse objects or put objects on your stack to try and keep the pressure off of your runtime to make your runtime work a little bit less and give more CPU time to the rest of your program. Okay, so with this, I do want to quickly get into a demo to go over some of these strategies we talked about in a concrete way with Grafana and Pyroscope, with one of our visualization tools that we provide from Grafana called Profiles Drill Down. So if we come down,
you accidentally stopped sharing.
Oh, let me quick share my. Sorry about that. Okay, hopefully that's better. So if we come over to our Grafana instance, we can open up the side panel, and under the drill down tab, we have profiles. And so profiles drill down is the tool we use at Grafana, like I said, to visualize profiling data in a variety of ways. So here, when we come to profiles, we can see that we're greeted with a list of all of the services that we're continuously profiling. And we can go and inspect any one of these services. We get a time series graph, which I'll discuss later, so you can perform kind of a high level at a glance analysis of how that service is behaving. For our purposes, we'll look at the checkout service, and we'll go click on this flame graph icon button to go look at the flame graph for this service. So once we're here, you can see that we have this timeline on the top, and we have the flame graph and top table on the bottom. And so this timeline, this is time dependent. So as we go left to right, we're going forwards in time. And what this value on the timeline refers to is this point in time's respective value for the total profile. So as we go along, we can see that if there are certain points where the profile gets larger, and so that means that this total bar here for this period of time will be larger than if we selected some period of time right before it. And so this can be helpful. You can see that we have a few spikes here, which can indicate that maybe there's something more work that's being performed by our application during these spiky times than during these more uniform low times. So that's the timeline. Now, if we move further down, we have the profile and the top table, like I said, or we have the flame graph and the top table. There's a few different things. There's a lot of buttons here. You can toggle top table only, flame graph only, or both. There you can. I think it often is easiest to look at both at the same time. But if you're, it can be helpful to look at the flame graph only because it does make it wider, so it makes it a little bit easier to dig into some of these more narrow frames. If that's something you might be interested in. When you're looking at this flame graph, the colors in the flame graph do have significance, and so in this default mode, the colors represent they're color coded by package. So you can see everything that's pink comes from this runtime package. Everything that's kind of like this like sea green or kind of pale green comes from the crypto package. This blue comes from this Pyroscope Go package. And so in the default mode, like I said, these colors represent the package that they belong to. You can change this, and you can change it to be color coded by cost. And so this might be the more familiar way that you've seen profiles in the wild, or flame graphs in the wild, where the more yellow something is, the smaller the cost, and it gets more red for greater cost. So this is another way of color coding these, color coding the frames. So we have this top table on the left, and this can be useful for browsing. You can order the costs of functions either by their self value or their total value, and so it might not be immediately obvious what the difference between self and total is. So self refers to how much time is being spent executing that frame in particular, whereas total is the amount of time spent executing that frame and all subsequent frames. So if we focus on this block here, we can see that this reports a self value of 210 milliseconds and a total value of 620 milliseconds. So that means the total width of this frame is 620 milliseconds of CPU time, and this bit that has no children right here is 210 milliseconds of CPU time. So the self value kind of refers to the work that this function in particular is doing, and the total is the work that this function plus all of its child functions did.
So if it's like colored based on like packages, and then those are both listed as runtime, are they coming from different places and that's why they're different colors, or what's making it different for the two different parts of runtime that are happening here?
Yeah, so I did a focus block, I focused on this block, and we'll get to this in a sec of what this means. But since I focused on this block right here, it kind of lightened all the other all the other frames. So that's why these colors change slightly. If I was to release the focus, you can see that all the subsequent colors back here are pink again. But since I focused, it changed the parent nodes a little bit, the color of the parent nodes a little bit, to reinforce that I was focusing on a particular block. Okay, so back to the top table. Like I said earlier, the top table is great for sorting by self and total. We also have a search function here. So I can search, maybe I care about my memory allocations, so I can search for malloc, and it'll do a regex match to find all of the mallocs, functions with malloc in it. And it'll also highlight those functions on the graph, or on the flame graph. And so this could be helpful if you have a very large flame graph and it's difficult to know precisely where your function is, but you know your function exists. So you might want to use the search bar on the top table, and that will highlight where these functions exist on the flame graph. And so once we've found a particular function, maybe I'm interested in this particular frame of malloc, I might care about more of this detail below this frame. But obviously it's too narrow, where it's very challenging to understand or just visually see what these very narrow flames look like. So I can click on this and select focus block, and that will zoom me in to have this block fill the total width of the flame graph. Its value hasn't changed, but its relative size has changed. And that's given me the ability to get access to see some of these more narrow flames that come off of it. So this focus block can be helpful to kind of zoom in on portions of the flame graph, so you have less noise you're looking at. Something that's interesting to observe here is that you can see the resolution of the profiler. So we have this runtime.getGC mask, and it reported to take 10 milliseconds. and same with this one, and same with this one. So you can see that these functions may have taken less than 10 milliseconds to execute in total, but we only can measure a resolution of 10 milliseconds. But as we collect more and more sample more and more stack traces, we can get a better and better understanding of the relative costs of these functions compared to the rest of the profile.
I have another question. So like right
Yes.
now you're looking at this and like, for instance, if you want to look at a specific area that you can do a focus block, but is there a way to be able to like zoom in more to be able to see like say all the gray areas and you're like, oh, I'm curious, even though they took so long, they didn't like they're not showing up right now, but is there a way to like be able to zoom into a specific area?
So there's no like click and drag and kind of box a specific area, but if you do want to see more about these gray areas that are difficult to see completely zoomed out, the best approach is just to focus in on a nearby block. So here I focused in on this block, and that kind of zoomed in all of those gray areas. Now I can actually see them color-coded pink. So this is obviously a lot of runtime work. And so that's the best strategy for um, bringing those gray areas into resolution. So another thing I want to show is if we search for, I know of a particular function here called place order. And so this is, I know, a function that is critical to how my application runs. And so I can focus in on this block and understand when an order comes in and now I have to respond to that request, I can get an understanding of what work is required to serve that request. And so here I can see we have a lot of regex matches. So this might be something I want to take a peek at, right? We clearly have we're clearly compiling a regex every time an order comes in, and so maybe this is something we can do to improve by perhaps compiling this regex once at the start of the application, and then reusing the compiled regex for every request instead of compiling it per request. There's another I just want to quickly, so there's another strategy we can use to understand the cost of a function, which is we can use sandwich mode. And so here I searched for this invoke function and placed it into sandwich mode. And what this does is it kind of gives us almost two flame graphs surrounding this invoke function. On the top, we can see all of the people who have called the invoke function, or all of the functions that have called us this function. And on the bottom, we can see all of the functions that invoke in turn called. And so this can be helpful, especially if you have a small function that gets called very frequently throughout your application. It can be helpful to understand where the cost of that particular function is coming from, and the total amount of cost that that particular function kind of, for lack of a better term, invokes, or the total amount of cost that that function requires to execute. And so here we can see that one of the functions who calls this invoke function is this metric service client export. We have another one over here, cart service client empty cart, and shipping service client ship order. And so we have three functions who call this function. And so sandwich view is really good at if you don't have one occurrence of that function in your flame graph, if you have many, many occurrences and you want to understand the impact of that function, kind of summed up, Sandwich View can help answer those questions. And so the last thing, one of the last things I want to go over is that we've been looking at CPU profiles, but you can, of course, switch to look at any number of different types of profiles. Now, the different profiling types you see here are going to be dependent on what profiling types your profiler supports. In the case of Go, it actually supports a wide variety of profiles. But for example, we could go and look at the amount of memory that was allocated for a particular particular application. And so we can see this flame graph represents this total amount of time here. And now instead of time, we're getting a measurement of storage, so gigabytes. And this, we can use this to understand, this function right here has consumed or has allocated about a gigabyte of memory in total. So that's this function and all its children. And this function in isolation has allocated about 700 megs of memory. And so this just illustrates that you don't just need to aren't just able to profile CPU time, but rather there's a wide variety of different profiling types that are available. And one of the last things I want to cover is that if you find a profile that is interesting and for whatever reason you want to explore it in ways that this tool might not allow, we have this ability where you can download a pprof. And so this will just trigger a download, and now you'll have the raw profiling data. And if there's a tool you're developing yourself or a tool that you know about that has some feature that doesn't exist here, you now have the raw profiling data for this profile here. And you can pipe that into the tool of your choice. So with that, I will.
I wanted to say one thing. Could you share your screen again?
Yes. Give me just a sec.
Thank you. Okay. Yeah. So for folks that are wanting to try things out, it's not the specific one, but if you go to play.grafana.com, you can go and play around with things. If you look on the top right here, especially if you're newer, or even just in general, there's the explain flame graph if you're going around on there, which can be super useful. So like, could you, for instance, just like click the explain flame graph for this one?
It'll take a sec because it's pumping through a lot of the data.
But yeah, so basically it uses AI, which everyone is talking about nowadays, to help explain what is happening inside of your flame graph, which can be super useful. But of course, it takes time. So yeah, I'm just going to put in play.grafana.com or .org, depending on it redirects. If you go there, you can play around with Pyroscope. You can go and explore. You can go into drill down. There's several different services and applications that are running over there for you to be able to try out. So there's like the Rideshare app, which is in the docs if you feel like going through the docs as well. And I guess right now it's being a little bit slower than normal.
Maybe we can debug on the fly. Oh, I fixed it. Yeah. So as Tiffany was saying, explain flame graph will send the flame graph or profiling data to an LLM that we and it will give us some hints and tips of things that we might want to look at to try to understand why the flame graph looks like it does, and if we want to make it better, how to make it better. And you can already see that, like I was saying earlier, it's identified that the regex compile is likely to be a problem. And in fact, during one of these recommended fixes, it's recommending we cache or precompile our regular expressions, which seems like a reasonable thing to do. We don't want to compile regexes in a loop.
And Robert's asking if you then need an LLM plugin for flame graph analysis.
Yes, so this flame graph uses the Grafana L1 plugin. So we don't call, just make raw calls to an LLM that you don't control. So the LLM plugin will manage which LLM gets called. You can bring your own LLM. You have finer control over how the LLM gets used and the data that gets sent to the LLM. Okay, and so with that, that is the end of our demo. And I want to thank everyone who stuck around to watch this and join us over at our Slack channel. You can find us in #Pyroscope on the grafana.slack.com Slack. Feel free to take a peek at our GitHub page, Grafana Pyroscope, and see what we have going on there. Or you can engage us at community.grafana.com.
And then, so Robert also says, if so, does it get hints about what language, Java, Go?
The short answer is yes. The longer answer is we don't in the prompts, we don't explicitly suggest which language it uses, but the LLM is actually quite good at inferring the language based off of the profiling symbols. So the Go symbols are quite unique. Same with Java or .NET. And my experience has been the LLM does actually quite a good job of understanding the language, the language of this program that got profiled.
Cool. Yeah, so please, come hang out with us in the Slack, ask questions there. We'll be posting when the next stream is, which is next month, and just details about that. And then there's also, the forums as well. So thanks for everyone for coming. If you thought this was useful, please share the link, which is going to be the same link with other folks that you know. So, and thank you so much, Bryan, for doing this today.
Absolutely.